Hello friends, today we'll solve the analog circuit problem. So GATE 2023 electronics and communication paper. So this is the first question. It is saying that in the circuit shown below, D1 and D2 are silicon diodes with cut-in voltage of 0.7 volt, and V in and V out are input and output voltages in volts. Okay, so we need to find the transfer characteristic of this circuit diagram. So four transfer characteristics are given. We need to find out which one is correct. So instead of plotting the entire transfer characteristic, you can observe that for V in equal to 0 volt, this is around like less than 1 volt. This is around for V in equal to 0, this is 0. For V in equal to 0, this is 1, and for V in equal to 0, this is minus 0.3. So just by putting V in equal to 0, we can find out which of the four is correct transfer characteristic. Okay, so we will use this thing. So whenever you can find one point on for which for V in where you can find the V out value is like different in all four cases, then you can solve for only that single point and convert it into a simple DC circuit. Okay, so when V in will be 0, what will happen is this diode is since connected, P side is connected to 0 and N side is connected to positive, so this will be off, and here P side is will be connected to 1 volt and D side will be connected to 0, so this will be on. So on means it will be replaced by 0.7 volt battery. Okay, so equivalent circuit will become like this. Okay, so this is D2, this is D1. Okay, now we just need to apply one KVL equation in this loop to find this voltage. Okay, so this will be like -1, and then it will be like I times 1k, then it will be 0.7 volt equal to 0. So this will be like minus 0.3 plus I equal to 0, so I will be like 0.3 milliampere. So since resistance are in kilo ohm and voltage are in volts, so I will be in milliampere. Okay, so this voltage will be therefore V equal to IR. So I is what, 0.3 into R is 1k, so this will be 3 volt this way. So this is minus to plus, this is plus to minus, so they will separate, they will subtract, so this will be like overall it will be V out is equal to 1 minus 0.3, so it is overall plus 0.7 volt. So this thing is only in option number 1. Okay, so this part is 1, so this is slightly less than 1. This is 0, this is 1, this is minus 0.3, so A is correct. Second question, we have a current mirror circuit based on MOSFET. He is saying that in the circuit below the voltage VL is, we need to find this voltage. Okay, so here you can see that there are two current mirrors. First is this one and second one is this one. Okay, so and this is the reference current source. Okay, so in current mirror circuits, like the current flowing in different branches is directly proportional to W by L value only, because suppose in this question like source and gate are shorted, so VGS is or VSG or VSG is same. Okay, so like ID current is like what, half mu n C ox W by L VGS minus VTH square. Okay, so half mu n C ox is same, VGS is same, VTH will be same, assuming all these are identical. So only current will depend only on W by L value only. Okay, so suppose these two are NMOS are there, so ID1 upon ID2 will be equal to W by L upon W by L of transistor 1 divided by W by L of transistor 2, like that. Okay, so I solved it separately also. So you can see that for like these two, we can say that I ref, this is the reference current, divided by W by L of this reference branch is equal to I copy 1 divided by W by L of copy 1. So you can see that I ref is 1 and W by L is also 1, so 1 by 1 is equal to I copy 1. I copy 1 we need to find out and divided by W by L of this transistor, so this is 10. So you can see that I copy 1 is 10 milliampere, so this is 1, so this will be 10. Similarly this is 1, so this will be 7 milliampere. Okay, so this current is coming as 10 milliampere, this current is coming as 7 milliampere. Okay, no current can go into gate, so no current can go in this one, so entire I 1 milliampere will flow down. Okay, similarly here also this 10 milliampere cannot go here, so it will go down only. Okay, now we know this is I copy 1 is what? I copy 1 is 10 milliampere, I copy 2 is 7 milliampere. Based on same logic, I ref upon WL by ref is equal to I copy 2 by WL copy 2, so I copy 2 is 7 milliampere. Okay, so this is 10 milliampere, this is 7 milliampere. Now again this current cannot go this side because both sides are gate, so no current can go inside gate, so 10 milliampere will flow into ground. Here this 7 milliampere will come, and now you can see that this is W by L is 5. Okay, so you can see that for this current meter, this is the reference branch. So here you can see that I ref upon W by L of ref is equal to I copy by W by L of copy, so I ref is 10 milliampere divided by W by L of this thing is 10 is equal to I copy. We need to find current in this branch, so that is I copy divided by W by L value 5. So you can see that I copy this thing is 5 milliampere. So 7 milliampere was coming from top, 5 is going down, so the remaining 2 ampere has nowhere to go except in this branch, so 2 ampere will flow like this. So therefore the voltage will be drop across this 1 kilo ohm will be 2 milliampere into 1 is 2 volts, so VL is equal to 2 volts. Okay, so this is the correct answer. Again easy question. Third question is based on simple op-amp circuit. So here you can say that we need to find the V out upon V in of this circuit. So here this is one part, here this is second part, and here this is third part. So this is a simple standard inverting amplifier, and here it is a standard non-inverting amplifier. So you can directly write this V1 voltage as minus R2 upon R1 divided by V in, and here you can also write it as 1 plus R2 by R1, 1 plus R2 by R1 divided by V in. So V1 and V2 are like very easy to find, or if you want then we need to solve this third stage only. This is also standard, it is a standard inverting summer. Okay, but let's solve this using KVL and KCL entire circuit. So when I talk about this stage, and this is V in given to minus terminal, and then there is this part. So here I drawn this thing separately to find V1. Then this second part also drawn like plus is going into the plus terminal and minus is like that. So here I will solve this part using KVL KCL, and then finally I will solve this third stage. Okay, so let's solve them using KVL KCL. So you can see here that this incoming current will be equal to outgoing current. No current can go inside the op-amp. Okay, it's an ideal op-amp. So I1 is equal to I2. So what is I1? I1 is V in minus 0 upon R1, and this will be equal to leaving current, so this will be 0 minus VO1 by R2. Okay, so V in by R1 is equal to minus VO1 by R2. So minus VO1 is equal to R2 by R1 times V in, so VO1 is equal to minus R2 by R1 times V in, which is the normal standard result for a inverting amplifier. Now for non-inverting amplifier, again we will use that we will apply KCL at this node, and using virtual short because of the negative feedback and ideal op-amp, this node is also V in. Okay, so I will apply KCL like V in minus 0 by R1. Okay, the sum of all the currents leaving a node will be 0, so this side is 0, this side is V in minus 0 by R1, and this side will be V in minus VO2 by R2 equal to 0. So this will be V in by R1 plus V in by R2 is equal to VO2 by R2. So V in I take common, so this will be like 1 by r1 plus 1 by r2, so this will be like or I will multiply r2 this side, so this will be like 1 plus r2 by r1 is equal to VO2. So this is again like standard result for a non-inverting amplifier. So now we are only left with this third stage. Okay, it is r2, r3, r3 and r4. Okay, so r3, r3 and r4. So here also will apply KCL. So this current plus this current will be like equal to this current, because no current can go inside op amp. So I1 plus I2 equal to I3. So what is I1? V1 minus 0 by R3 plus V2 minus 0 by R3 is equal to 0 minus V out by R4. So this will be like V1 plus V2 by R3 is equal to minus V out by R4. Okay, so now we can see that what is V, this is V1 means VO1 only. So what is VO1? It is minus R2 by R1 by V. Okay, and then what is V2? V2 is nothing but R2 by R1 Vn plus Vn. Okay, and divided by this R3 is equal to minus V out upon R4. So these two will get cancelled. So this will be basically V out is equal to minus R4 by R3 time Vn. So V out upon Vn will be minus R4 by R3. So that is your option number A. So this was again very easy question on op amp. Last question is like little bit tricky, theoretical question but conceptual. It is saying that in the circuit shown below, V1 and V2 are the bias voltage. Based on the input and output impedance, the circuit behave as which kind of dependent source? Voltage controlled voltage source, or voltage controlled current source, current controlled voltage source, or current controlled current source. So we can see that here the input is given at source and output is taken at drain. So gate is common between input and output, so it is a common gate amplifier. Okay, and one can remember that common gate amplifier acts as a current controlled current source, so therefore D is correct. Okay, but why common gate amplifier act as a current controlled current source is a good question. So we can remember that common gate acts as current controlled current source, and this common drain which you call as source follower act as a voltage controlled voltage source. Okay, so these two are very easy, and you can see that this common source can act as a voltage controlled current source, because depending on the voltage VGS, like ID value varies, so it is a voltage, it can act like a voltage controlled current source. Okay, so no standard circuit can, MOSFET circuit can like act as current controlled voltage source. It is little more typical. Okay, so these two like come in trans impedance and trans conductance, but these two are like straightforward. Common drain or source follower act as VCVS, and common gate act as current controlled current source. So to understand why it is so, let's first see what is the model of a current controlled current source. So I will teach you how to solve such problems. So current controlled current source, if you like simple model, then it is like this. Okay, so on input side there is a short circuit branch, and on output side, so it is current controlled, and this is a current source. Okay, on output side of a two-port network, where this current source value depend upon this current values. Okay, so it is a current source whose value is depending on current controlled. Okay, current controlled from input side. Okay, now since it's an ideal current source, but if it would be practical, then there will be a resistance also, because you know that in practical current sources there is a resistance also in parallel to this side. Okay, so you should know these four models, like current control voltage source is like so, and if there is a voltage controlled voltage source is like so, and this voltage controlled current source is like that. Okay, so these four standard models you can remember. Now, depending upon the input and output resistance of a circuit or a two-port network, we can find out which kind of control source it is acting. So if voltage control means we want maximum voltage to go into the input side of the two-port network, okay, and to get that we need like Rn is equal to infinite, okay, because if R1 is not infinite then there will be voltage division, okay. So if this side is like input side of this port is like have infinite resistance, then there will be no voltage drop across this Rs, which is a part of this practical voltage source. So all the voltage will drop across this side. So therefore voltage control means we want Rn is equal to infinite, okay. And so this is the thing about voltage controlled, means like we want maximum voltage to drop across the input port. So for that we need Rn is equal to infinite, so that all this voltage can drop here. Otherwise if it was finite then some voltage will drop across this part, so it will not act as a good voltage source, okay. Similarly, when I say current control, then this means I want maximum current to go inside the two-port network. So for that, what should be the ideal case? This should be short circuit, because otherwise there will be some current division, okay. But if it is short circuit, then all this current will go inside the network and it will act as a good current source. But okay, so because every practical current source will have some resistance in parallel to it, so for current controlled scenario we want Rn equal to 0. So this term means voltage control. Voltage source means voltage control on the input side, okay, and this is the voltage source, it is acting as a voltage source on the output side, okay. Now, so this was the thing, current difference between current controlled and voltage controlled. So current control means we want maximum current to go inside the port, so we want input impedance to be 0, Rin is equal to 0, okay. So this was the thing. Now if you look into the output side, then like it is current source, suppose it is a current source like current controlled or voltage controlled, then it means it is acting as a current source from the output side, okay. So it is acting as a current source when looking from output side. Now we want an ideal current source, but that is not possible in real life, so we will have some resistance associated with this current source. Now if ROC is infinite, then there is no problem, because all this current will go in, will drive the load, because our network block will be able to push all the or maximum amount of current into the load. But since some resistance is inadvertently, or we cannot remove this, okay, so we want ROC to be as large as possible with respect to RL. So we want this thing to be as large as possible, okay, so that it can act as a good current source. So whenever there is a current source like thing, so you can see that in both the cases, so these are current sources, so we want their R out to be infinite, okay. So we want this to be infinite so that all the current can go into the load and not into the this source, this R out thing, okay. So this is the typical thing. So now when we look into the common gate case, then you will realize that for a common gate what happens is that if you find it's simple, this is common gate stage where input is given at source and output is taken at drain. And if you find it's Rin, then you can see that to find Rin, what will happen, we will remove it and short or open all independent sources, okay, short all voltage source and open all current source. So and I will put Vx Ix, okay. Then you can see, and I will write the small signal model. So RD is connected to AC ground and this also connected to AC ground, and here I connect Vx and I find Vx by Ix. So you can see that Vx is minus VGS Okay, or VGS is minus Vx because this is source is connected between plus to minus, and here source is connected between minus to plus, so these are opposite polarity. So, and I can see that this Ix is equal to minus of Gm times Vgs. So Ix is minus Gm times Vgs is minus Vx, so basically Gm times Vx. Okay, because minus minus cancel, so Rin, which is Vx upon Ix, is 1 by Gm. Okay, so input resistance of a simple common gate is 1 by Gm. Similarly, if you need to find, now 1 by Gm is a very small value, okay, around 50 or 100 ohm, something like that, so which is considered very small. Now to find R out, what will happen, what we'll do is we will short all, this gate will be shorted, this part will be shorted, and from here we will connect Vx Ix at drain side. Okay, and this Rd will be also AC grounded. Okay, now again you can see that the source is shorted, gate is shorted, so VGS is shorted, so Gm VGS is 0, so it is like then what can happen, then this Ix current cannot go here because 0 current is flowing here, because VGS is 0, so all the current will flow in this branch, so Vx upon Ix is Rd only. Okay, so simple gate, common gate stage, you can see that 1 by Gm is the input resistance and Rd is the output resistance. Okay, or you can also remember it like for any MOSFET, like looking into the source it is 1 by Gm, and looking from drain it is very large or infinite, and looking into gate also it is infinite. Okay, assuming channel length modulation is neglected. Okay, now here you can see that there is one more Ri is also there because of this practical voltage source. So 1 by Gm was already there, now this Ri will be in series with it, so Rn is equal to 1 by Gm plus Ri, and R out will be like if you look into this side it is infinite, if you look into this side it is Rd, so again still it is Rd parallel infinite, so Rd still it is Rd only for this circuit also. Now you can see that 1 by Gm is a small, Ri you can see that for any practical voltage source, Ri the series resistance is like very small, so this is also taken to be small, so Rin is very small. And for V out you can see that Rd can be made arbitrarily large. Okay, so R out is large. Okay, so for this given circuit, R out is very large and Rn is very small. Okay, so you can see that R out is very large, Rn is very small, so therefore this will act as current control current source. So if R out is current source, means like R out has to be infinite and Rn has to be 0, so that maximum current can go into the two-port network, and R out has to be infinite so that maximum current can be pushed by the current source, dependent current source, into the load and not like into this R out value. Okay, so when Rn 0 R out 0, it is current controlled current source, and when both are infinite, and it is voltage controlled voltage current controlled voltage source. And for voltage controlled voltage source, ROC is 0, because voltage source on the outside on the output side means ROC has to be 0. Okay, and voltage control on the input side means Rin has to be infinite, so that maximum voltage can drop across the input side. Similarly, you can see that for this two more cases are there. Current control voltage source means ROC has to be 0, because it is voltage source on the output side, so ROC has to be 0, and current control on the input side means Rin has to be 0, so that maximum current can go into the network. And voltage control on the outside on the output side means no drop occurs across the series resistance which is there with the voltage source, and all the voltage drop across the load only. So for that we need the output resistance to be 0. Okay, so all four cases are there: 0, infinite, 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 0, and 0, 0. So this I have taken from like IIT Kanpur lecture on analog IC design. Okay, this is I think very important. So based on this table, we can decide by finding R in and R out, we can find out whether the circuit is behaving as current controlled voltage source or current controlled current source, voltage controlled current source, or voltage controlled voltage source. Okay. So these were all the 4 questions.